So, so we're doing an example problem here to explain the effect of using different number of bit analog to digital converters. So in this case, we're trying to measure two signals. Our input signal, first input signal is a 100 millivolt signal, or 0.1 volts. Right, and our second input signal is uh, a 1 volt signal. So for each of these different cases, we're going to use an analog to digital converter. One analog to digital converter will have 8 bits, all right, and then the other converter will have 12 bits. All right. In both of these cases, the range of the analog to digital converter is between 0 to 10 volts. All right, so it can be, for both of these, they can both measure a signal between 0 to 10 volts. All right. So the first thing we're going to do is we're going to determine our Q value, or our quantization level for the 8-bit converter, and we'll do the same thing for the 12-bit. Okay. So for the 8-bit converter, all right, the quantization level is going to be equal to 2. Sorry, it's equal to 10. The range of the converter, which is 10 volts, and we divide that 10 volts by 2 to the power of the converter, which is 8. All right. So in that case, we get 10 volts divided by 2 to the 8 is the same as 256. All right, so we end up getting a value of 39 millivolts per bit. Right? So basically, there's from that 8-digit number, that 8-bit binary digital word that will come off of the analog to digital converter, will each difference in value would be equal to 39 millivolts. For the 12 volt converter, same process, so it's the same range, 10 volts. Now it's 2 to the 12, the power, which would be 10 volts divided by what would it be? Whatever 16 times 256 would be. So anyhow, the math ends up being equal to 2.4 millivolts per bit. Okay. So if we end up so what we can, the second part of the problem asks us that once we determine the quantization levels, all right, we want to determine what is the quantization error. So to determine that, we're going to divide these numbers, the 39 millivolts and the 2.4 millivolts, by our two signals. So in terms of a percentage of the total value of each of our signals, we'll get these ratios. Okay. So in this case, our input signal for the 100 millivolt case, for the 8-bit converter, if we divide that 39 millivolts by 2 to get our quantization level amount, we get plus or minus 19.5 millivolts. All right, and if we divide that by 100 millivolts, all right, we end up getting, and then multiply by 100 to get a percentage, we end up getting 19%. So it's a pretty large error due to quantization. If we increase our analog to digital converter to 12%, 12, our quantization error drops to only 1.2 millivolts, and again we divide that 1.22 by 100 and multiply by 100%, we get only a 1% error. So much more reasonable error here. All right, but once we go to higher voltages, it makes a little bit less of a difference. We only have a 2% error for the 8-bit and a much smaller 0.122% for the 12-bit. So if you're trying to measure very small voltages, which sometimes we're doing, especially when we're doing things like thermocouples, which have very small changes in voltage, or what other types of signals have strain gauges, for example, have very small changes in voltage. So in those cases, you really want to make sure that your analog to digital converter is able to handle those effects. So the two ways to get around it is to either use more bits or use a smaller range of signal that better captures the data that you're interested in. So keep those things in mind when you're picking different data acquisition devices. Consider the number of bits as well as the range that those bits work across.